This is the Proton Guru video practice for topics 1.1 and 1.2. These problems will give you practice on applying Coulombic forces and representation of structure, assigning polarity and dipole moments, and formal charge. Some brief and straightforward reading to get you ready for these problems can be found in lessons 1.1 and 2 in the Organic Chemistry 1 Primer 2018. You can also find additional chemistry videos and information on how to match the videos to your particular course's textbook at protonguru.com. This first problem asks us to provide a suitable Lewis structure for our neutral compound with the formula CH2N2. The first thing to do when you have a Lewis structure problem is to find the Lewis symbols for each of the elements involved. Here we need the Lewis symbols for carbon, hydrogen, and nitrogen. The easiest way to find the Lewis symbol accurately is to look at the periodic table and to count the tall columns. So if we have column 1, hydrogen is in column 1, and we give it 1 dot for its Lewis dot structure. If we count over 1, 2, 3, 4, only counting the tall columns and omitting these, the fourth tall column has carbon in it, so we add 1, 2, 3, 4 dots to the carbon to produce its Lewis symbol. Finally, with nitrogen, we count 1, 2, 3, 4, 5 until we get to nitrogen, and we give it 1, 2, 3, 4, 5 electrons, making sure we only pair up electrons once we filled all 4 of the sides with at least 1 electron first. Once we have those Lewis symbols, we can then figure out how many electrons total these atoms will contribute to the Lewis dot structure. The 4 electrons from carbon, we have 2 nitrogen atoms, so a total of 10 electrons from the nitrogens, and 2 hydrogens, so 2 electrons come from the hydrogens, to give us 16 electrons we must use in our structure. Next, we can assemble the core of our structure, as I've shown here, just by putting single bonds in. We're told there's a CH2 unit and then there are 2 nitrogens coming off of that, so this is a reasonable way to start out our structure. Now we can start to use our Lewis symbols to give us more information. The carbon should have the ability to make 4 bonds, and we've used 1, 2, 3 of the carbon's electrons to make single bonds with the hydrogen, but the carbon has a 4th electron that it hasn't shared with anything yet. We'll make that rather bold right there. If we assess the use of electrons from the nitrogen atoms, and each nitrogen atom should have 5 electrons to contribute, we see that we've used 1, 2 from this nitrogen, so it should have 1, 2, 3 left over. The nitrogen on the end here has used 1 electron to make the bond. It should have 1, 2, 3, 4 more left over. When you have unpaired electrons left over in Lewis dot structures, you can start to use those electrons to make multiple bonds. We could make a multiple bond between the nitrogen and the carbon, or between the nitrogen and the nitrogen. If we consider both of those cases, we see now that this carbon has 4 bonds and has used all 4 of its valence electrons to accomplish that, so that carbon is done contributing to the structure. This nitrogen has made 3 bonds and has 2 electrons left over as a lone pair. The nitrogen at the end, however, we haven't accommodated. We might need to add an additional multiple bond in this structure. If we look over here, where I've instead made a multiple bond between the 2 nitrogen atoms, we can then fill in how many electrons are left. I've used 2 of this nitrogen's electrons to make the bonds, 3, 4, 5. And this nitrogen again only has these 2, and this carbon has this 1 electron. And we could make 2 multiple bonds in our initial structure between the 2 nitrogens. There's our 2 bonds there, that double bond. Or in our alternate structure, we could add another bond between the 2 nitrogens over here. So we have these 2 structures, and instead of leaving any electrons unpaired, I've added a pair of electrons in the spots that are required to give an octet to every atom in our structure. We'll be doing more formal charge practice later in this video, but right now we can count up the formal charge and add those charges. And for all the non-zero formal charges, I've written down the equations: the valence minus half the bonding electrons minus any non-bonding electrons. If you don't know how to assign formal charges, we're covering it later in the video. So let's recap this answer and see what the procedure is to get these types of problems correct. First, use the periodic table to get the Lewis symbols. Next, assemble the base structure having only single bonds. Next, pair up electrons to make multiple bonds to what extent is possible. And then you can pair up electrons to make lone pairs to give atoms octets where necessary. Finally, you'll want to check your structure for correct electron count and then assign formal charges. Now let's talk about dipole moments. And here's a typical type of multiple choice question found on standardized tests, asking you which molecule has the largest dipole moment. Well, to correctly assess the dipole moments, you're going to have to think back to general chemistry and the valence shell electron pair repulsion theory, or VSEPR theory, to figure out the shapes of these molecules. And we'll cover how to figure that out in a different video as well. For now, we'll just provide these shapes for you. Now, you need polar bonds in the molecule if you're going to get a dipole moment for the whole molecule, but none of the bonds here are very polar. The carbon-hydrogen bond is nonpolar. Next, we look at this case with the fluorine-carbon bonds. Those are very, very polar, so we'll draw in the little dipole moment for each of these bonds. But if two bonds are pointed like this, they will add together to create a vector of addition here. So both those two bonds together will lead to a net dipole for both of those bonds pointing in that direction. Now likewise, you take a look at these two bonds, and they're pointed at angles a little bit towards us and a little bit away from us. So those two carbon-fluorine bonds lead to an addition vector for a dipole for those two bonds only, going this way. Now if you have a pole that way and a pole that way, those will cancel out. So just as in the case where you have nonpolar bonds, if you have a bunch of polar bonds but they pull in all different directions, they can cancel each other out. And that's also what happens down here. Carbon-oxygen bond is also polar, but carbon dioxide is a linear molecule. So one dipole pulls to the left, one pulls to the right, and they cancel each other out. So there's a zero dipole moment as well. What about this case that I skipped over here with two hydrogen carbon bonds and two chlorine carbon bonds? Well, the carbon-hydrogen bonds are not polar, so these don't contribute to the molecular dipole. These carbon-chlorine bonds, though, are polar, and they pull in those directions. The addition of those is that the net dipole moment for that molecule will point in between those two chlorine atoms. This is the only molecule that has a non-zero dipole moment. So just to recap this, the way you address this type of problem is you first determine which bonds are polar, and you draw arrows towards the more electronegative of each of those atoms. The sum of those bond-dipole vectors is equal to the molecular dipole. And remember, bonds having these dipole moments can cancel each other out to lead to a net molecular dipole moment of zero. Here's a little bit more complicated version of that type of problem. Which molecule has the largest dipole moment again? And again, we'll have to draw these out, and these molecules all have a tetrahedral shape. So we have a net dipole moment of zero in cases where you have a symmetric distribution of all the same type of atoms around a central atom in the tetrahedron. Now, on the previous problem in this video, we saw that the CH2Cl2 molecule has a net molecular dipole shown by this arrow. Now, we, by the same rationale, say, well, these carbon-fluorine bonds are polar, and the sum of those two vectors would also be a molecular dipole moment in that direction. So which has the largest dipole moment if both of these molecules have a dipole moment pointing in the same direction? Well, this is where the problem is a little bit more complicated than what we saw in the previous one. The carbon-fluorine bonds are more polar, so we'll draw a larger dipole moment for those two bonds than the carbon-chlorine bond. The sum of the carbon-fluorine bond would lead to a molecular dipole that is larger in magnitude because of the larger magnitude of the vectors we're adding together. So the largest dipole moment would go to the CH2F2 molecule, so choice D. And just to recap how we address this type of problem, you need to determine which bonds are polar, draw arrows towards the more electronegative of these, looking out for the canceling out of bond dipoles when you're thinking about the molecular dipole. The sum of the bond dipoles is the molecular dipole, and you have a non-zero sum in these two cases. Sometimes they'll tie if you're just looking at the direction of the dipole, and in that case you have to know that the more polar bonds lead to stronger bond dipoles. Now, earlier in the video we solved a Lewis structure which required us to look at formal charges on some of the atoms. It might be a good idea to review the way that one assesses formal charges, and in organic chemistry you'll need to really quickly figure out what the formal charge is so that you can move on to more involved parts of the problems at hand. This problem also gives us some practice with line bond structures, where we have to remember that the ends of lines or the bends in lines, or anywhere where two lines come together, those represent understood carbon atoms. And if you have a molecular symbol drawn, you have to draw any hydrogen atoms that are on those atoms. But if you have a carbon that is sitting at a vertex, you assume it has the correct number of hydrogens on it to get its octet or to accomplish whatever formal charge is given for you. Now, if we think ahead to how to figure out formal charges, we need to know how many bonding electrons are around that atom. So the first thing we're going to do is draw in all the hydrogen atoms that are not drawn for us explicitly in the line bond structure, but which are understood to be there in those structures. So I'll go ahead and fill those in. You'll really need to be able to do this quickly to accomplish organic chemistry problems that are more complicated. So go back and make sure you can do that. But once we have these hydrogens drawn in, now we can take a look at the periodic table. And what we're going to do is draw the Lewis symbols for each of the atoms. And I've gone ahead and done that for all the atoms that are featured in that large group of molecules on the previous page. We have some molecules with hydrogen, boron, carbon, nitrogen, oxygen, and bromine. And by counting over to see how many electrons you would have in the valence shell, counting only the tall columns, 1, 2, 3, 4, 5, 6, 7, we can figure out the Lewis symbols. The Lewis symbols give us really important information for this type of problem, because now we know what those atoms will look like in a usual neutral structure. Every unpaired electron in a Lewis symbol is capable of being shared with another atom to make a bond, so hydrogen should make one bond and have no lone pairs. Boron has 3 of these unpaired electrons, so it should be able to make 3 bonds with no lone pairs in its usual neutral structures. Carbon should have 1, 2, 3, 4 electrons to make 4 bonds and no lone pairs in its usual neutral structure. Nitrogen has 3 unpaired electrons to share in its Lewis symbol, so it should be able to make 3 bonds. But it also has a pair of electrons that will be staying on that nitrogen as a lone pair. Now look at this oxygen. It's only got 2 unpaired electrons, so it should make 2 bonds in a usual neutral structure, and it should have 2 lone pairs in those neutral structures. A really good example of this is water, where pretty much everyone knows is H2O. It's got 2 H's on the oxygen. For the octet, it's got to have 2 lone pairs. That's really a prototypical usual neutral structure for oxygen. And finally, bromine has only 1 unpaired electron, so it should make 1 bond in its usual neutral structure and 3 lone pairs. Once we have all that information in front of us from looking at the Lewis symbols, we should be able to figure out which of these atoms in all these molecules over here might have a non-zero formal charge. And if we look at the hydrogens, every hydrogen in this whole set of molecules only has 1 bond and no lone pairs on it. So none of the hydrogens should be necessary for us to evaluate to see if it has a formal charge other than being neutral. So we can also rule out any carbon that has 4 bonds and no lone pairs, like this one, or any of the CH3 attached to some carbon units. Most of these atoms in these structures will have a formal charge of 0. If we find the examples in these cases of atoms that don't adhere to the usual neutral rules we figured out from the Lewis symbols, like this oxygen. A normal, usual neutral state for oxygen would be 2 bonds and 2 lone pairs, but this oxygen here only has 1 bond and has 3 lone pairs. So I've gone ahead and evaluated this, and you should go back and make sure you can figure that out as well, where I've just put all the atoms that don't adhere to the usual neutral state, and I've made them red in this example now. So we have to remember how to figure out the formal charge. You'll see some different ways to represent this equation, but the formal charge is really how many valence electrons the atom has to start with in its atom, minus the number of bonds it has, minus the number of non-bonding electrons around it. In this case, it's all lone pair electrons. So let's take an example such as carbon. This carbon has 4 electrons. We get that from the Lewis symbols that we've already figured out. So it should have 4 electrons when it's neutral, and it's, in this case, shared 3 of them as bonds. So subtract 3 bonds. And it has 2 non-bonding electrons. The electrons are on the carbon, but they're not in a bond. 4 minus 3 minus 2 is minus 1. And you can go through and do this for all of these. So let's illustrate at least one example for each of the atoms we have featured here. So here's an oxygen. Oxygen has 6 electrons around it in its Lewis symbol, 6 valence, minus how many bonds does it have? 3, minus these 2 non-bonding electrons that are here as a lone pair. So 6 minus 3 minus 2 equals plus 1. If we take a look at this boron atom, boron has 3 electrons in its valence shell, minus 4 bonds, and there aren't any lone pairs. So 3 minus 4 minus 0 is minus 1. That's the formal charge for that boron. Nitrogen has 5 electrons in its valence, as we know from the Lewis symbol, minus 2 bonds, minus 4 electrons that aren't in bonds is minus 1. Last atom to take a look at would be bromine. Bromine should have 7 electrons. Here we're sharing 2 with other atoms to make bonds. And we have 1, 2, 3, 4 electrons left on the bromine that aren't making bonds, that adds up to +1. One other example I want to take a look at is this one right here, this carbon. Carbon has 4 electrons in its valence shell. It's 4 minus 2 bonds minus 2 electrons that are not in bonds. That formal charge is 0. So it's not the usual neutral state for carbon, but it is an unusual state that happens to still be neutral. So the formal charge on that carbon is 0, even though it's not the usual sort of carbon in a neutral compound we're used to seeing. So on this answer recap page, I've just taken the opportunity to fill in all the correct answers. You want to maybe work these on your own, see if you can get these answers, and just want to recap the procedure. It really is helpful to figure out the usual neutral form for each atom from the Lewis symbols. Then we can assess only those that are not the usual neutral. And using this equation, formal charge is valence minus bonds minus non-bonding electrons, you can quickly figure out what the formal charge is on any atom in any structure.